Swayam Prabha. Digital India. Educated India.
So good morning everybody. So today again we'll continue with classification. And did you remember yesterday we said that we can use different kind of models. So which has a probabilistic interpretation, we have seen it yesterday. So we are maximizing the posteriority and we are minimizing the loss on what we have defined on how to predict the posterior distribution of class. And then I said there are other models where we'll be selecting the best classifier from a set of classifiers. So here we'll today talk about one such classifier which is called decision trees. You'll see that this is more intuitive and this is more sync with the human thought. So we'll learn what is the decision tree and then how it's used for the classification task and how to learn a decision tree. And to define a decision tree, we need few terms to know. That is, one is more important is information gain, and how we use this concept of information gain for and use it in the decision tree. So I'll come back to this slide again. Let's see here. So this is again from the same data, that iris flower data. I have selected two features. One is sepal width and other is sepal length. And these three are the three classes. Blue is setosa, and then green and red is versicolor and virginica. Now yesterday we have learned linear classification. So here if we try to draw some linear classifier, we'll be having like one line here, maybe this type of line which will separate this blue class from the green and red class, and maybe some line here which will separate the both green and red. So but in that case, if we think about this, so we have few blue point here and then few red point here and then few green point here. So when we are saying our classifier is this line, this we say that something like you can think about some alpha 1 or some weight of W1 on sepal length plus W2 on sepal width plus some again W0. If this is greater than 0, then we'll say it is a setosa. And if it is not, then it will be two other classes. So but what do you, is there any meaning you are getting from this equation? That's you have like maybe 0.2 of sepal length, 0.7 of sepal width plus 0.5 which is greater than 0, then it is a class. So, but this is like less intuitive. We can say that, okay, for being if this is a high one, this is maybe 0.7 and this is 0.2, then we can say for this, maybe this feature is more important kind of. But still we cannot say. So when we humans say that this I want to classify, then how we classify? That we want to classify among these things, then we'll say that okay, if the sepal length is greater than something, then it will be the versicolor, and if the sepal length is less than something, then will be in the setosa. So this is like we understood more betterly if we do the classifier like this. So in decision tree, we'll be doing like that. So every times we'll be selecting some features and then we'll be dividing the samples according to that feature value. So in that case, instead of this kind of line, we'll be having maybe one line here. This I will say this is more like setosa and this side is more not like setosa. And then maybe we'll again divide it in somewhere here. So that we'll say that this is setosa and this is this square, this grid, this box is some versicolor, and again this block we cannot say much here, but this there you can say this is versigynia. So but now the difference is this is not now the linear classifier. So these boundaries are not linear, but it has more interpretations. So that is why it says like it involves segmenting the predictor spaces into number of simple region. So how we are defining the region only depending on putting some threshold on the features. And it is simple and useful for the interpretation. Now it is giving better interpretation, like if you check the sepal length and it is less than this, it is check the sepal width, it is greater than this, and then you can say it is a setosa. So here, like example what I have already talked, that we are first dividing it like this. So, okay. So here we are saying that if the sepal length is less than 5.45, then it is more green color it is getting, that it is has a high chance to being setosa class. And it is, if it is not there, then it is high chance for being virginica class. So here we cannot say much about the versicolor class if we divide it. Why? So okay, here you just now ignore the term Guinea. We'll explain it later. So think about the first node where we have the whole space. And what is the number of sample? Number of sample is 120, and there we have the classes 40 from the setosa, 39 from versicolor, and 41 sample from virginica. When we divide it, the space with this line, with this feature, then we get this left hand side had 37 of setosa and 1 or 7 from the other classes. So we have, if we take the majority vote for unknown point there, then you will get the more versicolor. So if we have some points here, we can say back according to the majority vote of that node of the training sample, we can say this is more setosa. If you have some point here, then you know it's not the setosa because of it's only have 3 sample from setosa, this region. But it may be either of others two, virginica or it is a versicolor. But here the virginica is little high. So if you take again the majority vote, virginica has a 40 samples, versicolor has 33. So if you take the majority vote, you will get the label as virginica. So again we can divide our space like this, and we can then go down and make our tree. So ultimately at the end we'll get this 5 region in our space, and each region will give some, we'll annotate it with some of the classes depending on the majority vote. It is clear what is majority vote? Okay. So now in this tree we split every node it splits and it goes to the end node, and then these end nodes are denoted as a leaf. When your data points comes to a leaf, then you can give a label to the data point. And here we have 4 interior node and 5 leaves. So how many leaves you have? You have that many sub-region in your space. So but how we know that where to divide it? How to break this region? So the basic idea of the decision tree that we want to divide the predictor space into the aim non-overlapping regions, like you can say R1 to Rm, and every observation falls in a given region Rm is giving us same predictions, same colors depending on the majority vote. So we can have the regression decision tree and the classification decision tree, but here we will be talking more about only classification decision tree. So tree can make only the rectangular regions. They cannot make any slight, any lines which is not perpendicular of any of, which is not parallel to any of these axes. Always the decision boundary will be parallel to some axis. And it's fit greedily. So once a split you made, depending on whatever the decisions, whatever the major criteria you take, you split a feature and you make a 2 region after that, on that, and then you cannot delete that split. You cannot undo that split. So it is a greedy algorithm. You don't know whether that split is actually better or not, but you have to go for that one. And we have to somewhere stop the splitting. We cannot continue split for infinite time. So we'll go to how to split these nodes, how to select those thresholds. Before that, we'll first talk about how to predict a test data point if you have a decision tree. So if you have an unknown test data point like this magenta, then you have to start from the root node and take the decision whether it should go to the left node or the left child or the right child. And then you go according to the decisions. So for here, we first went to the right child because the sepal length is more than 5.45. And then again there we have that way this a division over the sepal length, and then it is again it goes to the right side. And then we found that is a leaf node and which has more virginica samples. So we say that magenta or the test point has the class label virginica, right? This is just how we put the class to the, how we find the majority vote. So I think up to this, it is clear to you. It is very, very intuitive, nothing mathematical. So now we'll learn one very initial and the classic algorithm which is called ID3, and it is a top-down greedy algorithm to build a decision tree. But this algorithm has some restrictions. So after that, some new algorithms comes, that is a CART or C4.5, and those things we'll learn later. So what is ID3? ID3, in every node, you begins with a root node, and root node has all the training sample D. Do you remember what was D yesterday? This is a set of training samples which has a Xi and a Yi pair. We have n number of training samples, and we put all the samples in a root node, and then we choose unused attributes or unused feature. Which feature is already unused for the decision tree, for the decision making. And we select the best feature, and then we create the new children's or new descendant depending on the number of value that features take. So if the feature takes A1, A2 and A3, he will be creating 3 subnodes, and you will give if A is equal to A1, then it is the left side. If A is equal to A2, then it is a middle subnode. If A equal to A3, then it will be the right one. So now here we are assuming that all features are categorical. So every features can have up to k category, k values, and then for every feature, that feature which has k values will have the k subnodes or k branches. Now you put all the samples with that satisfy that decision, you put in these subnodes. So your sample now has, your whole space has been divided in these subnodes, maybe in 3 subnodes. And then you continue it again with the subnodes. So if you find another, now A is used, you cannot use A anymore. So you have to take some other feature to divide the left subnode. You can take other feature to divide the middle subnode and the right subnode. So these features may not be the same. So you can select B for the left subnode, you can select C for the middle subnode. But after some times you have to stop splitting. When you can stop? So if there is no node in that subnode, then you can, it automatically you will be stopping there because it is a failure. This leaf does not have any sample. We cannot break that. And if a node has only one label, if you got some subsample in some node and that has only one label, then you are sure that that box or that rectangle has only this sample. So no need to divide it anymore. Yes. Yeah, I'll come later. How to select best attributes. Yes, I'll be explain it later. And then, otherwise, if then and in that case, he will be given the label node as the samples from where this region has, or samples are coming from the one label. So we'll put label that subnode or leaf node as that label, that output. And sometimes he will not break again if at all there are mixed samples, but will not break it because we'll see by breaking it we are not able to do much better. So how it will be? So if we have some places like in, so if you have something like this and also like this. So how many, if you get some node, it is showing these regions. Again you want to break it, you will not do better. So you break break whatever you want to do, but you will not do much better. You will be getting the probability distribution in the sample will be in this region or rectangles will be same. So then also we'll stop. Now it's coming to the questions, then how we'll be deciding that which break is a good break or which break is not a good break. So how we can break the attributes. So here we'll take one example. So here we are given that this is a 4 predictors we have, 4 features. One is outlook, other is temperature, other is humidity and the windy. And all are the categorical features. They can have only few values. And then target is the whether people will play the golf or not. Okay. Now let's see how to make this decision tree. So one very crude criteria is that you take a random feature and break it. That you can do. Another thing is that people usually do, okay, who has the least number of categories, take that. Maybe some features had 2 categories, some features had 3 categorical value, then we'll take the least one. Other heuristic attributes is take the features which can break your tree in the most number of subtrees, so that which has most number of attributes. Most number of values. These are the heuristic, and you don't know whether that will be good or bad. Now other things we can do is that we can break the tree depending on the something it is known as the information gain. So whether we are gaining some information by breaking the node. How to define the information then? So do you know any measure of how you will be knowing whether some space has a informative space or not? Do you have any? Okay. So maybe I would like to have your answer. So you tell me. I'll draw two pictures. So can you tell me that whether this R1 or this R1 dash has more informations when you are doing classification task? R1 has more information. How do you know that R1 has more information? So we are talking only the R1. So R1 has only one class. Samples from one class, so we have more. So you can think about then the how will be your class level are mixed. That is one criteria, right? So before going to define you this information again, one more things I want to tell you here. We all know that we need some regularizations for the generalization performance. Here also, in machine learning, it is always like that you use less resource to build your model. So for decision tree, it will be better to have smaller tree among all the trees which divide your space correctly. So now you have a set of decision tree and you have to pick the smallest one among the all correct trees. So, but this problem is a NP-hard problem, this combinatorics problem. So we will do it in a greedy way by using this information gain theory. We'll select the attributes which will divide the node into sub-nodes, where the sub-nodes has more information or it has less impurity. Got it? So how do you calculate this impurity? One is the classification error rate. What you said, that one side has only one class and other side has other class and it is not mixed. That is one criteria we can use. So do you remember what is this? This is like in the M region, what is the amount, what is the probability of getting Y class. So this PME, it is defined as this PMY. It is like the number of nodes with yi equal to y. They are, and xi belongs to this Rm, and total number of node in where xi belongs to Rm. So if you the what fraction of nodes which are in Rm region has Y label. The fraction of nodes which are in Rm region has Y label. So this is going to give you the misclassification rate, because you will be classify these subnodes as all have the Y which is maximum Y. So now what is this? So if in some node here we have 2 blue and maybe 3 3 blue and maybe 1, 2, 3, 4, 5, 6 red. So what will be your G of, so G of X here, red or blue? According to the, what will be your predictions? The class level you will be predicting for this region. According to the maximum majority vote? Red. So this will be the red. So what is the amount of misclassification you are doing here then? You are doing the misclassification is 1 minus 1. So it will be 1 minus 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 minus 3 by 9, or you can say it's a 6 by 9, right? And other thing is Gini index. So it is actually calculated, it's like this. So you can see it is a PM 0, 1 minus PM 0 plus P1 M1, 1 minus PM1. This is the Gini index. Okay. This is how we calculate the Gini index. This is also give you one impurity measure. And other is the cross entropy. So it is giving the how much information is there, is the entropy shows you according to the Shannon's theorem. And then how much is the cross entropy is present is also say you the what is the impurity. So in ID3 we mainly use the cross entropy information gain. And now what is the information gain?